So the equations of motion we derived were the following. So we had the time derivative of the height plus the x derivative of the height times u must be equal to 0. That's conservation of momentum. And then the other equation was the time derivative of h times u plus the x derivative of u squared h plus a half g h squared. Okay, you can sort of see how this is somehow connected up with the, so this is conservation of mass and this is conservation of momentum. This is somehow connected up with the energy and all that stuff. So we can simplify the equations. I'm not going to go through all this, but we can take this equation here and we can convert it to the time derivative of u plus u times the x derivative of u plus g times the x derivative of h equals 0. Alright, and then we introduce this. There's a few bit of a process here, and again I'm not going to go through all the details of it, but we introduce, this becomes going to become super important, we introduce this c, which is the square root of gh, and it's the linear speed. So basically, and then you can work through this and derive the system of equations. It's not super important at the moment that you do this, but you end up with the system of equations here. That's equation 1, and the second one is the time derivative of u plus u dxu plus 2c dxc equals 0. Okay, so this is the so we can transform the system of equations by introducing this variable here, which is the square root of gh, or if you like it, c squared is gh squared. Sorry, gh. Now, the most important thing for you to understand at this point here, where we're going to go here, is what is this? The most important thing to understand here is that h is a function and c are functions of each other. See, so h and c are determined together. So once you know, while it says like you're finding a speed. So if you know, okay, I know I'm getting into the danger zone here, but if you know c, then you can follow that you know h. All right. So let's just go back a second here, and then, well, we've got this system of equations, and we're going to start to work with the system of equations and try and solve it. And that's when we get into this characteristics and all of this stuff here. So I'm just going to do one more. So we haven't really got started yet. We're just deriving the equations. So we're just going to do one thing here with this linearized equations, and it's easiest to do it if I just do a bit of clearing here. I'm going to get rid of this log. Okay, magic has happened. So now I'm going to write down the linearized equations. So these are the linear equations for shallow water. And they are themselves kind of interesting. I've actually written quite a few papers on them, but linearized equations. So what that means is we can start this anywhere, but remember this is equation, now we've written them as this is equation 1 and this is equation 2. So when we linearize, we basically get rid of we basically get rid of multiplications by this term here, multiplication by u. and we set up here that we say u is small, okay, but h is not small. H is equal to h naught, this reference des, plus h, see what notion I call it here, plus zeta. Okay, so the depth of the water can be big, but so we've got basically flat water, and we've got a little rippling here, which is zeta. Okay, which is the difference here. Okay, so zeta is small. So if I substitute in that, d by dt of h is going to be d by dt of zeta, and I'm going to get h times u. So what I'm going to get here, perhaps I better write this out fully rather than jumping to it. I'm going to get h times u, d by dx of h times u. So I'm going to get h naught plus zeta multiplied by u equals 0. And I only want to retain I don't want any term that's a small times a small. So if I get zeta times u, that's going to be small times small, that's going to be vanishingly small. So the only term I'm left with is the time derivative of zeta plus the x derivative of u multiplied by h naught. Okay, because everything else is going to be a small times a small quantity equals 0. That's the linear equations, the first linear equations. And the second one, I'm going to get the time derivative of u and this term here is going to be small times small. I'm going to get gravity times the derivative of x with respect to, so I get plus gravity times dx of zeta equals 0. So this is the linear system of equations, the linearized shallow water equations, and these can be combined together. So if I derive this with respect to t, I'm going to get so if I'm going to combine them, I'm going to get the second time derivative squared of zeta plus, I'm going to take a time derivative into here, so I'm going to get dx of the time derivative of u, and the time derivative of u is minus g times the x derivative of zeta. So I get dt squared zeta minus g h naught dx squared zeta equals 0. And that is, of course, hopefully I haven't gone into the danger zone here with my head. That's the wave equation. And its solutions are f of x plus or minus ct, where c is the speed and is the square root of gh naught. So that's why we use this notation for c being the speed. It's the local sound speed, and it's very much like the equation of gas dynamics, where c is the speed of sound in the rest media. So the equation is, these nonlinear equations are about the way in which the sound speed is altered in some sense. Alright, so those are the linearized equations. We're not going to talk too much about those and how to solve them and all that stuff. You understand how to solve the wave equation, you've done all that stuff, but we're not going to use any of that here. We're going to go and do these nonlinear equations.